I'm Mr. Douglas.
Hi, Walter. How are you?
Good, how are you?
Good. You have a good weekend?
Yeah, it was pretty good.
You get more snow?
Not really, no.
Oh, you did. Okay. I thought it was gonna go through your area, but I guess it did. All right. There we go. There are the other guys.
Yeah.
Hello.
Hello.
How are you?
Oh, good.
Good. You have a good weekend?
Yes.
Good.
Got it. Wait. Got it.
Get more snow?
Maybe like a little. Not at my place, but yeah, very
Little.
very little.
Very little.
Yeah.
Okay. That's good. So you're not slipping and sliding on the roads anymore.
Nope.
Uh, okay. Let's get started. I wanted to I haven't looked yet at the proofs that you did, but I think that would be useful um, to see how you're doing with them. So, um, can we go to Adobe Connect Tuesday? And Walter, you've had trouble sharing your screen in the past, is that right?
Yeah, my computer's probably not high powered enough.
I see. All right, that's too bad. Um, Okay, you send me. I'll be able to just get yours up, um, and I'll share my screen with yours. That's what I'll do. Um, but Ryan, you can start. Let me get this correct. So yeah, okay, I got the right screen. Share entire. I have to share through BlueJeans first, so it gets recorded, and then I go here. And I want to make you guys presenter. Oh, I'll make Logan a presenter, and I'll make Ryan a presenter. Okay, and I won't worry about Walter because he can't do that. And so, okay, so we're ready. So, Ryan, can you share your screen and get up the document that you submitted that has a proof?
The mid section one or the mid segment one or another one.
Let's start with the mid segment, sure, and then let's go to the others.
Okay, one sec. The pop-up's coming up.
All right. Logan, did you finish your homework?
Yes. I emailed it in earlier this morning. I forgot to email.
Okay.
I'm sorry.
That's all right. So you'll go next.
Okay.
And you got my email.
Yeah.
Okay, good.
There we go.
Okay, good. It's happening.
Here's the
Okay.
I guess I'll start out with I remember in the when we started proving quadrilateral or special properties of a quadrilateral or quadrilaterals, you had a lemma 2 where
it's called
lemma 2.
Yeah.
Yeah. Where if you you rotate a line about a point that's not on the line or the line segment that 180 degrees, then the result the image will be parallel to the pre-image.
Yeah. Yeah.
So I use that to show that DE and AB or AC were parallel.
What point are you rotating around?
The intersection point of the diagonals of the quadrilateral ADEC.
Yeah. Okay. Well, you don't know that that's going to map into AC. That DE is going to map into AC if you do that.
Okay.
So that's an issue. Logan, do you have a different thought?
I sort of went off the SAS theorem that we talked about earlier, and I said that because of this theorem, A, B, and C and the triangle, the larger triangle dilated, are similar triangles. And I said it's dilated by a scale factor of 2 since the triangles are similar. And then I said that the length of the side that's the joiner of the midpoints are parallel, and that the longer one is 2 times longer than G.
Why is it?
Because the dilation. Here, hold on a sec. The triangles are similar, and B, the angle of B lies in the same point as the smaller triangle and the larger triangle, since it's dilated from point B, or from the point that's dilated from. And so that means... Actually, that doesn't make sense now that I'm explaining it. I managed to prove that they're that the longer one is 2 times the size of the other. I didn't prove that they were parallel.
Okay. Ryan, do you have a thought about how to prove they're parallel?
Can we say that since since they're that all those A, D, B are collinear, and that when a dilation preserves, or I'm not sure.
Well, you're on the track. What is...
A dilation preserves collinearity and parallelism, right? So,
yes. Right.
So we would say we would consider a dilation by scale factor of AB over DB.
Yeah. Right.
And that would, of a triangle, or not triangle, I don't know. Yeah, I think you'd just go from there, and then
of triangle. Yeah, triangle what?
I think it's BDE.
Yeah.
And that
from what point?
From B.
Okay.
And that would map D onto A and E onto C.
Mm-hmm. Mm-hmm.
And since dilation preserve parallelism, AC L to DE.
Yeah, it's just be careful about. Well, let me leave it to you. Walter, you with us?
Yeah.
So, what I want to say is, what does dilation preserving parallels mean?
I mean, if two lines are parallel in like a pre-image, they'll be parallel in the image.
Okay, so that's not quite what's going on here. So how do we say this, that that, and what theorem are we using to say that AC is parallel to DE?
Oh, well, dilation preserves angles, so angle BDE is equal to angle BAC, and angle BED is equal to BCA.
Mhm.
And then basically the transversal BA cuts the two lines with the same angle, so they have to be parallel, right?
Yes. Yes. And the other thing is, do you guys remember the fundamental theorem of dilation?
Not really.
Yeah. Get up your theorem list and look at that.
There we go. So CI.
So that first sentence
Okay.
says that the image segment is parallel to the pre-image segment. That's not the same as dilation parallels. Dilation preserves direction, one can say. And it also preserves parallels, but it's different. Preserving parallels are relationship. So that means, as Walter said, if two lines are parallel in the pre-image, that's the relationship of parallel. Then in the image of those two lines will also be parallel.
Okay.
In this case, it's preserving the direction, so to speak. In other words, the image segment is parallel to the pre-image segment. So the direction is the same. But that's not the same as preserving parallel, which is a relationship. Direction is an attribute.
Okay.
Okay?
Mm-hmm.
All right, good. So the fundamental theorem of dilation could have given you right away that they're parallel.
Okay.
Because the image line is parallel to the pre-image line, period. And it's double the length because that's also this is a direct consequence of the fundamental theorem of dilation. You can also do it with SAS, just like you did. SAS similarity also works. And you can use what Walter said about the corresponding angles basically being equal because dilation preserves angles.
Okay.
Okay. All right. Logan, let's see one of your proofs of the either a property. So yeah. So Ryan, you have to relinquish sharing your screen, I think, and then Logan shares his, and then just get up the document that you submitted with either a proof of a property of a quadrilateral or a proof of if certain things are true, then the quadrilateral is special in some way. Okay. Okay. Can you make it a little larger?
Oh.
Okay. Good. That's good. Great. Okay. Talk us through it.
I was trying to prove a kite, and the way I approached it was
Well,
that
let's look at your theorems then. First.
yeah.
Well,
I
go ahead.
said if a shape, or this shouldn't be shape, this should be quadrilateral. If the quadrilateral has two separate pairs of adjacent congruent sides, the quadrilateral is a kite.
Okay. All right.
I needed to use this lemma, which was that isometries preserve collinearity and betweenness, or at least the one that I was using.
Okay. You don't have to state it, and once we have, we've proved that. So you can just now use it. You don't have to state it and have a proof and do any of that. Once we prove something, it's there. You just use it.
Yeah.
And reflection preserves distance. Yeah. Did you read the comments that I?
Yeah, I did. I haven't corrected it yet.
Okay. All right. So talk about that. Talk about what reflection preserves distance is a what?
Well, why reflection preserves distance, or
No. Well, what kind of is it? Something we have to prove?
no. Well, we've already proved it in the past. So.
Not quite.
So
What
I should
is it?
put.
What is it? Ryan, do you know?
An isometry?
Walter?
It's an assumption, right?
It's an assumption. That's right. It's an assumption. It was it was a basic assumption that we made. So it's not proved. We can't prove it. It's a basic assumption. Reflection preserves distance was where we started. So that's the thing on the ground floor, the basic building block. So it's not a proof. It's not something you can prove. It's just there. That was one of our assumptions. Okay. Sorry. Now go on.
Okay. So I took a triangle ABC.
Okay.
And then you use any of the segments as a line of reflection. I used BC here.
Okay. I'm sorry, I have to stop you because I have to ask you what assumption you're making. You said two separate pairs of adjacent congruent sides, but which ones? Which ones are you assuming to be equal?
Any of them, really. It's just any two separate pairs. I mean, it could be the ones in the original triangle or in the reflected ones.
Oh, you're starting with a triangle.
Yeah, triangle ABC.
I see. Okay, I'm sorry. Now I understand. Okay, go ahead.
And then I reflected it over one of its sides.
Okay.
And that's where the reflection preserved distance and angle comes into play. So I said, because of this, it has to have two separate pairs of congruent sides. And okay, and also since it's reflected over a line, and the line and two of the points are on that line, they have to be adjacent. And I said, since this situation that I described to you has, or this shape that I described to you, at least has two pair of congruent sides, then it has to be a kite. Yeah.
Okay.
Yeah.
All right. Comments from Brian or Walter?
Was this where we're going from one of the properties to, or one of the properties of like a kite, and then trying to prove that it has a line of symmetry? Or,
Yeah.
So,
What's our definition of a kite?
it has A quadrilateral with one line of symmetry, opposite vertices.
Yeah, going through opposite vertices, right. That's our definition. And so if it says the quadrilateral is a kite at the end, then that's what we're trying to prove.
Yeah. So I guess since instead of starting out with a triangle, you need to start out with your the property that you wanted to do. So like two separate pairs of adjacent congruent sides. You start out with that instead of the triangle.
Yeah.
Okay. Walter, do you agree, disagree?
Yeah,
Pardon?
that's where you need to start with the quadrilateral instead of the triangle.
Okay.
Yeah.
All right. Logan, do you understand that?
Yeah.
Okay. So basically, I think kind of what you did was almost, instead of, if you had started with a quadrilateral, you almost proved the converse of this. You kind of assumed that, yeah. But anyway, you have to start, that's the point, is you have to start with a quadrilateral with two separate pairs of adjacent congruent sides, and you have to name which ones they are.
Yeah.
And then you prove that it has a line of symmetry.
Yeah.
Okay, good. Okay, Walter, I'm going to get, so can you stop sharing your screen, Logan?
Yeah.
And then I'm going to share mine and get up Walter's, and Walter can talk us through. So I'm going to share my screen. And now I understand what happened is it minimized. I couldn't find it. That's why. And now I have to do it again in Adobe. Finally got this figured out. And this is what I want to share, main display, which is this. Yeah. I'm going to share this. Okay. And then now I can close this. It minimized it. That's the deal. and now I get up Word, and I am going to, don't need that. And this will be later, if we get to it. You don't have to. So I'm going to open, not this, but 7th homework, Walter's, and Walter, which one is it?
Oh, I think it's the 24th.
24th, okay. All right. So now I want to make it bigger. Is that big enough, or you guys want 200 maybe? Yeah, that's good.
Yeah, that's fine.
Okay. All right. So I'm just going to skip a line here so we can. So this is what you're doing, right, Walter?
Yeah.
Okay. So
Yeah.
talk us through this.
Alright, so my theorem was that a parallelogram has opposite congruent and parallel sides.
Okay.
So I just start out with the definition, which means that parallelogram has twofold rotational symmetry.
Mm-hmm.
So under a half turn, that means opposite sides are mapped to each other.
Uh-huh.
And since rotations preserve distance, that means that these opposite sides have to be congruent.
Mm-hmm.
And then alternate interior angles are also mapped to each other through this half turn.
Mm.
And since rotations preserve these angle measures, these alternate interior angles have to be equal, and so the sides are parallel.
Okay. Comments from Ryan or Logan?
Maybe just a diagram.
Yeah, I think so too. That would be nice. Because I'm having trouble following it without a diagram. So I'm going to, I'm not going to save this, but I'm going to put in, there is a parallelogram here. Under, I don't want you, not now. I don't want this now. Thank you. Let's go back here. Okay. So under shape, there's a basic shape, and this is a parallelogram. And make a parallelogram like that. And it's yeah. Well, I'm going to show the paragraph mark so I can put that down. Okay, let's make this a little bigger. Now, if I right-click and I go to Format Shape in Word, if you didn't know this kind of stuff, I don't want any fill. And I also, this always makes a shadow, which I hate. So I get rid of the shadow, and I want this to be black, not blue. Okay. And so there is a parallelogram. And I'm going to just label the vertices so we know what. So, I'll call this A. And then, sorry, let's just take a second. There's A, okay? And I'm just going to copy and paste it a few times. And we'll call this one B. And I'll move A over here, B over here, and C over here, and D, there we go, over here. Okay, so I think we're all good on the sides. Now, okay, now this part here. What are the alternate interior angles that you're talking about?
BAC and ACD.
BAC and ACD. ACD?
Yeah.
Oh, ACD. Oh. So you want us to draw AC? Is that correct?
Yeah.
Okay. All right, so we'll get a line here. And unfortunately, it does this bizarre stuff. But that's all right. We'll fix it. And I'm not going to bother to, make it pretty. Okay. So now, what alternate you're talking about? Say again, the alternate material angles you're talking about.
BAC is mapped to ACD under the half turn.
This one here is mapped to this one here, and those are alternate interior angles. Okay.
Yeah.
And they're equal because rotation preserves angles, and therefore these lines are parallel, and you can do the same thing. Okay. Ryan, Logan, does that make sense now?
Yeah.
Yeah.
Happy with that? Okay. So, Walter, a diagram. Gotta have one. We can't follow it. And you didn't say anything about drawing AC, but now that we see that you draw AC and do it, then fine. Okay. Is there any other way to show that the opposite angles are equal without drawing AC? So let me take this out.
Well, I mean, angle A and angle C is equal. And angle B and angle D are equal, so...
Because?
Rotations preserve angle measures.
Sure. Done.
So, do we know that the sum of the angles is 360? Can we use that?
Do we have to? Why can't we say that A equals C because rotation preserves angle?
Yeah, I know, but then you have to. I'm just talking about angle D and B now, since
rotation preserves angles.
Yeah, but we don't know the measures of those angles, so we can't. I was gonna use a supplementary argument about how A plus D has to equal 180, and so the lines are
I
parallel, but
understand, but do we have to know the measure if rotation preserves angles? That just means that the image angle is the same as the pre-image angle.
yeah, for sure.
Isn't
Yeah.
that enough?
I'm not following.
Okay. When we rotate this around the intersection of the diagonals, angle DAB goes into angle BCD, doesn't it?
Yeah.
And therefore they have to be equal because rotation preserves angles.
Yeah.
So that proves that whole angle A is equal to whole angle C.
Yeah.
And that's what you wanted to. Oh, you said. Oh, I see. You said parallel sides. Okay, I'm sorry. I was
Yeah.
confused. I thought you were saying that. Yeah, I'm sorry. Okay, that's my fault. Now I understand. I didn't look carefully enough at your theorem. I apologize. So that's how you prove the parallel sides. But so I was saying that you can also prove that. I thought you were saying opposite angles equal also, but you weren't. Okay, got it. All right. Good. All right. Let's. I apologize for that. Let's look at your second one.
Okay.
Let me make. Yeah. Okay. And let's kind of use this diagram and see what's going on. Okay, go ahead. What's your theorem first?
If the opposite sides of a quadrilateral are parallel, then it's a parallelogram.
Okay.
Okay. Wait, okay, I messed this one up then.
Okay. Why did you mess it up? Describe.
Yeah, I proved the converse, I think.
Yes.
Yeah.
Yes. You
I
started
guess,
with our definition of a parallelogram. Yeah.
yeah, I guess I could do it right now then.
Okay.
Okay.
This one was actually done. This was the example in, and it wasn't all that easy, I think. But this was the example that was done on what's it called? Symmetry definitions and properties document. Pretty
Oh,
sure.
okay.
Pretty sure this was the one that was done there. So, all right. So as long as we're here, let's take a second to look at it. Let me get that up. And it will be in one of the earlier classes. Try this. Oh yeah, back more. Got 17. There it is. Let's make that 200. Go down here, all the way to number 6. Yeah. See? If opposite sides of a quadrilateral are parallel, then the quadrilateral is a parallelogram. That was done there. And the lemma was, that if you turn it, a half turn maps a line into a parallel line. And then here's the proof. So let's go through this. This is useful. So let M be the midpoint. So draw a diagonal. Let M be the midpoint of the diagonal. Then make a half turn around M. And since M is the midpoint, that means A has to go into C. And then the image of the line, since it's a half turn, the image has to be parallel. So this goes into a parallel line. Yes. And similarly, this goes into a parallel line. And Now there was, and then we proved that D is the image of B because B is on line AB and line BC, and therefore the image has to be on both the parallel images. So a D has to be on both the image of AB, which is DC, and the image of BC, which is AD, and those two lines intersect at just one point. So it has to be D. I think that is, so therefore not only does A go on to C, but B also has to go on to D, and therefore it has twofold rotational symmetry. That's not so easy, but that's the argument. That's at least one argument. Do you have a different argument for that, Walter?
No.
Yeah, okay. All right. So, okay, are there any more proofs that we could look at? I'll close that. So this is it that we haven't looked at that you guys have done?
I think I have one.
Okay, Logan. I'm gonna get back to here, and I know I have to get this back up. Now I know what the story is. It minimizes it. Okay, so I'm gonna stop sharing here. Okay, and now you can share your screen, Logan.
Oh, Ryan was gonna do something.
Oh, Ryan. Okay, Ryan. Okay, sorry.
Yeah, I'm just trying to find the right file.
Okay.
I think it's a different day. Please be the right one. I have a cleaned up version of the square.
Good.
Proving that they're showing that the midpoints that I didn't prove last time.
Okay. So yeah, so good. Here we go. Okay.
So last time, I was trying to prove that, or I was trying to show that the theorem, if all sides are congruent, then the quadrilateral is a square. And I set it up like this.
Okay, wait. Hold it a second. Mm-hmm. Is that true? If all sides are congruent, then the quadrilateral is a square?
No. You need some other things in there.
Yes.
Oh wait. I guess that, yeah. Okay. But I can show that it is because the definition of a square is two lines of symmetry going through opposite vertices and two other lines of symmetry going through the midpoints of opposing sides.
Right. But hold on a second. If you only assume that the sides are equal, mm-hmm. then what does it have to be? Doesn't have to be a square.
No.
What could it be?
A rhombus?
Yeah, it could be a rhombus. And a rhombus only has two lines of symmetry through the...
vertices.
Yeah, and so that's all you'll be able to do. You won't be able to show the other set through the sides.
Okay.
Because it's not true.
Okay.
Okay, so there's a flaw there somewhere. All right, we'll figure it out. Okay, so this is not so easy. But I think this discussion was useful. Okay, so why don't you stop sharing and let me share my screen.
Okay.
Okay, thank you.
But I had a different one.
And I'll make comments on not what I wanted. Okay. Oh, my screen is being shared, it says. Okay. So let's see. Don't want this. We're not going to get to this. We're not going to get to this. That's okay. We are going to get to this. All right. So I sent you guys. Is it big enough? Let me make it bigger. I wanted to go over this. Are there any questions on the sheet? Which gives you and have you made an appointment, or will you make an appointment to take the test?
Yeah.
We have a test.
Yeah.
Test needs to be taken by end of day Friday.
I think I can do it Thursday. I think I'll be able to make an appointment soon.
Okay.
I have to make up one other test and then I can do it.
Okay. You may need a little more than an hour, just to be safe. And Walter, you'll be able to make an appointment?
Yeah, I just did.
You just did, great. Okay. You want me to go through this? Have you looked through it, or what? Where are we?
I think I can look through it on my own and send you some questions if I have any.
Sounds good. Okay, so this is just like last time. This is the structure of the test. So I tell you what's going on, each of these, okay? All right. And if you have questions, then ask, and I'm happy to spend time with you. All right, I'm not going to do this now except to just say that I assigned you 6. So I'll look at what you did, and this method, there will definitely be a problem like this. And you guys seem to be doing pretty well on them now. The last few I've seen have looked quite good. So I'm happy with that. All right. So maybe we will have time for this other thing. So let me just say that. Sorry. Yeah, I did want to look at the right thing. Yeah, I wanted to talk about this. So this is the 3D figures, and there will be a question on this kind of thing. I don't want to spend all the time going through all these things, but is there any particular one in number 3 that
with the tilings?
Yeah.
Or the tilings and tessellations, I think, in 3.
Yeah, right. Where is that?
I think it's one of the last.
It's the translation office.
Yeah.
Right. Let me get down here. Yes. Okay.
The last one.
Mm-hmm.
On the 3D. When I was trying to explain, when I was trying to interchange the word plane when it says indefinitely to fill the plane without gaps or overlaps. What would I put instead of the plane?
Who has a thought? Logan or Walter, do you have a thought?
I ended up just putting infinite box.
Okay. All right.
Yeah, just space probably.
Space, yeah.
Okay.
Space is probably the best word.
Okay.
Do you know a shape that tiles space?
Wait, what?
Can you think of a shape that tiles space?
Cube.
Cube, yeah. There are others, but it's, well, what else? Yeah, okay, cube, what else?
Tetrahedron.
Yeah, might. I'm not sure. Okay, so these are harder. A box, or a rectangular prism certainly does. You can, but the tetrahedron might, so all these things might, and those are not obvious. So this is a lot harder than
pyramid.
Yes. Okay, it's a lot harder than 2D. All right, I wanted to go over 5A and B quickly.
Okay.
So, yeah, we have time. So here is a regular square pyramid, and this is the definition. The apex is right above, so to speak, the center of the base. If you draw an altitude is a segment from the apex perpendicular to the base. Then it's going to hit the base. It's going to intersect the base right at the midpoint. All right, so reflection symmetry. Can you describe some reflection symmetry? Let's just rotate around. So anybody can start, but then somebody else has to go. So just one description of reflection symmetry.
A plane that runs, or that includes the apex and the midpoints of opposing sides.
Okay. Agree? Everybody agree with that?
Yeah.
Okay. So how many such planes are there like that?
2?
2.
Yeah, so there are 2. So there are 2 planes of symmetry, just like Ryan said. Okay, somebody else. Is there more reflection?
Yes. Through the apex and opposite vertices.
Okay.
At the base.
Okay. So through this point and this point and this point. How many of those are there?
2.
2 of those. Okay. Is there any more, Logan? Is there any more reflection symmetry?
No.
Okay. Is there any rotation symmetry?
Yeah, just the one as the altitude, but.
Okay. So around the altitude, and what else do you have to say to describe it? The altitude is the axis.
Well, the axis of rotation is the altitude.
Yes, that's true, but what else do you need?
Fourfold symmetry?
Fourfold
rotation.
Right.
Yeah.
That's right. Fourfold rotational symmetry around the axis. I was looking at some videos. Some call it rotational symmetry of order 4. Another way to say the same thing. But you do have to say that. You have to reference the angle in one way or another. Okay. All right. So let's go to the regular tetrahedron down here. Not too far. There. All right. So anybody? Reflection symmetry. Is there any reflection symmetry in the regular tetrahedron, which has equilateral triangles for all 4 faces?
Playing through 2 vertices and the midpoint of the opposite edge.
Okay, so 2 vertices and the midpoint of the opposite edge. Do we agree that that'll be a plane of symmetry?
Yeah.
Okay. How many such planes are there?
4?
Why 4?
Because that's how many different apexes there are.
6.
Oh,
How many different what?
never mind. I don't.
Okay. How many, Walter?
Oh, there's 6.
Why are there 6?
Oh, you can pick any of the 6 sides. 6 edges for the plane to go through.
Right. See, each one of these talks about one edge. So, 2 vertices and 1 edge, and there are 6 edges to do that with. So for every edge, there are two opposite vertices. So if this were the edge, then these would be the opposite vertices. So these two vertices and this edge. Okay. And the midpoint of that edge. Yes. Okay. So there are 6 planes of symmetry. Notice that for these, it's really nice to have models. So, okay, maybe I'll add that to the homework. Can you guys buy flex straws? A box of flex straws?
Like just straws or
straws, plastic flex straws. The flex straws have
yeah.
They bend. They bend
Okay.
on the top. They're usually for kids. You can make with just flex straws. You can make these things, and then you can really see them, and that's useful. So I'll put that. If not for next time, but for the time after next, it would be good to have that, and then we could really discuss it and see. Okay. Axes of rotation. Through the through the apex and the center of the base. So how many? And what do we have to say about that?
That it has threefold rotational symmetry around that axis.
That's right. And that's also an altitude. So how many such axes of threefold symmetry are there?
4.
Yeah, and how come there are 4, Logan?
Because there's 4 vertexes to the opposite side.
Good. Okay. All right. Good. So we did A and B. Watching the time. All right. I'll just. We're not going to get to this, but I'll just. Well, actually, I'm not going to say this. I will say something, and what I'll do is I'll put this part on the homework, which is easy. This is just the making part. After we make it, then we'll be able to, and if you do get a chance to get some flex straws before Friday, that would actually be nice. But if you don't, I understand. So this sheet, it turns out that this is an interesting topic that we can do quickly. There are what are called symmetry groups of figures and 2D and 3D figures. And that means that you can compose symmetries by doing one after the other. And you can and what is a group? Do you know what a group structure is in advanced mathematics or not?
Yeah, it's closed, it has an identity as an inverse, and it's associative.
Right. So it's like, for example, numbers are a group and they're a commutative group, which means that it's commutative, obviously, under addition, right? You can add numbers, and it's closed, and the order doesn't matter. It's associative, and you can make a table, a table of addition. That's an infinite group, but these are finite groups, and they're interesting because they're studied a lot in not only mathematics but in chemistry and all these other things, all these other fields. So you make an equilateral triangle, and this is how this is easy to do, and you label the vertices, and it says you can put 2 sides of a cardboard triangle together, or you can just stiff paper if you have it, otherwise regular paper, but you have to label it on both sides. Basically, you cut out a large triangle and you label it on both sides. So A matches A, B matches B, C matches C. And what's this? Oh, yeah. And then, okay, wait a second. Paste these 2 sides of the cardboard triangle over and paste the cardboard triangle on this base. I see. Because we want to keep track of the movements of the triangle. So we're going to have vertices 1, 2, 3. So you don't cut out anything here. We're going to have vertices 1, 2, 3, and we're going to place A, B, C on top of it, and then move A, B, C around by reflecting or rotating, and see what happens. Does A stay at point 1, or does A go to 3, or what happens? And then the composition of reflections and rotations, all of them symmetries, will yield a group structure, which is kind of interesting. So I'll just have you make it. So what you do, I'll just say it again, make sure you understand, is you make this 1, 2, 3 here is not to cut out. This is just this will just be there for you to use. But you do want to cut out or make separately, whatever, an equilateral triangle ABC, and you want to label it on both sides. So you can do it with 2 pieces of paper, or you can label it on both sides with 1 piece of paper, whatever you want. Any question?
Nope.
Is that clear?
Yeah.
Yes? Yes? No?
Yeah, that's fair.
Okay. So that'll get us ready for next time. So we can do that. I was going to do more, but we're not. Okay. And then the other thing that I'm going to assign is, so we didn't talk about it today, but that's okay. It's not this. It's going to be in the homework, not the class. As we'll end here. Is this sheet that I made from Henry. And this is just a review of complex number basics. It's this 1, 2, 3, 4, 5, 6, 7. That's all. And it's not bad. It's something you've had before, so it's not. But we're going to use complex numbers to compute transformations, which is really interesting and a lot of fun. And it goes beyond, I think, what some of you have seen before. Okay. All right. We good?
Okay.
Any questions about anything? Because we're just...
No questions. Did he try?
Oh, I think his webcam must have cut out. Yeah, I think his webcam cut out.
Oh. Okay.
Oh. Okay.
Bye.
See you on Tuesday then. See you next. Yeah. All right.
Yeah.
Bye.